Hello and good afternoon. In this video, I'll be talking about my presentation for my use case, that is LPG leak detection system using weight monitoring. Now we know that LPG or liquefied petroleum gas is widely used as a cooking fuel, and despite being such widely used all around the world, it has its fair shares of risks that it comes with, due to which at times these risks outweigh the merits that the cooking fuel comes with, which is being an easy to source cooking fuel. And uh, the one of the major risk with it is, since it is stored in such a high pressure, even the smallest leak can cause huge accidents. And even though modern solutions tackle it to some extent, like some buzzer system that goes off, some alarm system that goes off when it senses LPG gas leak, they often have many limitations. This presentation will give a brief overview about the proposed solutions and how it works. The solution basically works by identifying the abnormal patterns in the weight of the cylinder. Now we know that whenever we use cylinder, it loses its weight gradually, and the system that I hope to implement uses senses these abnormal patterns. It essentially, yeah, it identifies these patterns and it triggers a gas sensor, which upon detecting gas leaks takes actions such as turning off the gas regulator, turning on the exhaust systems, cutting off electricity, and sending the alert to user. This was a really brief introduction to it. I will be talking more about it in the next few slides. Now, the problem with traditional LPG safety is that first is high risk factor. LPG cylinders are common sources of house fires and explosions, with thousands of incidents reported annually in India alone, which I have thoroughly talked about in my research report. Second is that the detection systems are very limited. Existing solutions typically only generate alarms or notifications and requires users to take action in order for the disaster to be prevented. It just generate an alarm or a notification, and it requires user to come and maybe turn off the gas regulator, or open the windows to direct the flow of contaminated air outwards. The third is delayed response. The traditional gas sensors get triggered when the concentration of leakage exceeds a certain threshold value, which takes some time, that might that some time potentially increasing the risk. That that some time that we are talking about here can be very crucial in the time of disaster, and if we can save even a few seconds here and there, it can potentially save lives. Now, energy efficiency is another problem with the traditional LPG safety. Current system continuously run gas sensors are generally higher powered. They require higher power. The sensors that I have used in my report usually consume a lot of power, and without actually the power that the traditional methods consume, they use the power without actually giving any additional benefits. Now, here are some previous research reports. Some of them used wireless sensor networks, like using a mesh of wireless gas sensor nodes. Other used Arduino based systems or load cell monitoring and ventilation integration. I've used these as my inspirations, as my I have cited these papers in my own research, and I have taken them as a base to build upon. And now our system, the basic components that goes in it are the major three components that we will be talking about here is the Arduino Nano 33IT. It is a low powered board and has a built-in Bluetooth and Wi-Fi connectivity. It also has 256 kilobytes of flash memory, and the compact size makes it easier to integrate even in the smallest models, like ours in this case. Strain gauge load cell. It is a transducer that converts the force applied to electrical signals and provides weight of the cylinder. It will be kept under the cylinder and it will be constantly measuring the weight of the cylinder. Now, the third sensor is the TGS 2620 gas sensor. It is a semiconductor sensor that detects the concentration of LPG in air with high accuracy and is only turned on when anomalies are detected, which I'll be talking about in the next slide. Now, the way the system is implemented is, first I've broken down this system into three phases: the monitoring phase, the detection phase, and the action phase. In the monitoring phase, the weight is continuously being measured using the load cell, which is then digitized using the ADC converter, analog to digital converter. Then is the detection phase. the the data of the weight of the cylinder is constantly being worked upon and constantly being the auto correlation method is constantly being used on the data that is collected using the load cell, which identifies abnormal weight changes, and if there are any abnormal weight changes, it triggers the sensors and flags it as an anomaly. Now, the third phase is the action phase, where all the actions take place. Automated safety responses, including valve closure, power cutoff, and exhaust activation. The system in itself is really energy efficient because the actual gas sensors are only turned on when anomalies are detected, which is which is taken care of using a relay switch whenever there is an anomaly detected. Whenever there is an anomaly flagged, the relay switch turns on the our gas sensor, and then it starts checking if there is a gas leak. And before it actually senses a gas leak, the valve of the our cylinder is already turned off to make sure that even if there is a gas leak, the source of the gas is being shut down. So the damage that has already been done does not get any worse than that. And then if the gas sensor actually senses any gas leak, then it takes actions, and if not, the system will go into recovery mode. And since the system works with weeks and months of data, it can detect abnormality before it gets out of control. And even if it does get out of control, it does not get any worse than what the situation already is, and then it just gets better from that. Now, the system workflow again: weight monitoring, anomaly detection, gas sensing, and safety actions. Load cell continuously measures cylinder weight and sends data to the microcontroller after digitizing it using analog to digital converter. The weight data is received constantly, analyzed using autocorrelation method to detect any abnormal trends. Upon the detection of the anomaly, the gas sensors are turned on to detect any gas leaks by checking the concentration of LPG in air. Lastly, upon leak detection, the servo motor rotates to close the regulator valve. SMS is sent to the users, the exhaust system is turned on, and the electricity is to that area is cut, so that if the user comes to, let's say if there is a gas leak in the kitchen and the user comes and tries to turn off the light switch, then it has a risk, that it has a potential risk that that switch can be the ignition source and can cause a house fire. Now, these are the budget considerations. This is the budget breakdown. Arduino Nano 33 IoT costs the most, which is around 3,000 rupees where I live. The load cell, the converter, the gas sensor, servo motor, relay module, and uh, other miscellaneous expenses, which ultimately takes us to around 6,000 rupees per unit. And this is the future scope and the conclusion. It can be more cost optimized. The integration of AI and machine learning algorithms can drastically improve the performance and reduce the false alarms, as it can work on huge amounts of data, and it can work on that data more efficiently. And lastly, advanced sensor networks Multi-sensor nodes can improve the accuracy over larger areas like factories or godowns, like one used in a study that I've cited in my report. That was it for my presentation, and that was it for the use case. And I have included all of this in my research report as well. And yeah, that's it. Thank you.